Hello, everyone. Today we are going to talk about genetic quantization-aware approximation for nonlinear operations in transformers. Slide 1. Motivation, optimization of nonlinear operations in transformer-based models is crucial due to their high computational cost. The inefficiency of these operations hinders the speed up of transformers on various hardware platforms. There is a pressing need to facilitate the deployment of transformers on edge devices. Slide 2. Previous works have attempted to approximate nonlinear operations like JLU, softmax, and layer norm with quantization-aware 32-bit integer int32 arithmetic. A neural network-based general LUT approximation framework, NN-LUT, was designed to tackle computational overheads. Some methods have simplified the above by factorizing floating-point data and performing single-entry LUT approximation on the mantissa in a small range. Slide 3. Limitations of existing approaches. Existing methods lack generality as each optimized operator contains distinct computational data flow. The LUT in nitrogen mononitride LUT contains numerous parameters that are independent of the input data range, leading to resource wastage. The nitrogen mononitride LUT struggles to encapsulate the variation in the representation range across layers unless subjected to calibration, a process that is time-consuming. Slide 4. Need for a new approach. The limitations of existing methods necessitate a new approach that can handle the computational overheads more efficiently. The new approach should be able to manage larger scaling factors and should be efficient for hardware design with compact resource utilization. The new method should capitalize on low-bit integer arithmetic to overcome the constraints of existing quantization algorithms that fail to adjust parameters by scaling factors. The authors of this paper are addressing the challenge of optimizing nonlinear operations in transformer-based models. This problem is significant due to the high computational cost associated with these operations, which hinders the speed-up of transformers on various hardware platforms. The need for optimization is further emphasized by the desire to deploy transformers on edge devices, which have limited computational resources. Previous attempts to solve this problem have involved approximating nonlinear operations like JLU, softmax, and layer norm with quantization-aware 32-bit integer int32 arithmetic. A neural network-based general LUT approximation framework, known as nitrogen mononitride LUT, was also designed to tackle computational overheads. Some methods have simplified this approach by factorizing floating-point data and performing single-entry LUT approximation on the mantissa in a small range. However, these existing methods have several limitations. They lack generality, as each optimized operator contains a distinct computational data flow. The LUT in nitrogen mononitride LUT contains numerous parameters that are independent of the input data range, leading to resource wastage. Furthermore, the nitrogen mononitride LUT struggles to encapsulate the variation in the representation range across layers unless subjected to calibration, a process that is time-consuming. To overcome these challenges, the authors propose a new method, a genetic quantization-aware algorithm called GQA-LUT. This method automatically determines the breakpoints in LUT approximation for nonlinear functions. It also manages larger scaling factors by implementing an algorithm that images the fixed point FXP conversion as a form of mutation to boost accuracy. This approach is designed to be efficient for hardware design with compact resource utilization, capitalizing on low-bit integer arithmetic. The author's key insight is that the scaling factor in quantization is a crucial element that significantly impacts the precision of approximation parameters. They found that larger scaling factors lead to less accurate approximations. Their proposed method overcomes constraints of existing quantization algorithms that fail to adjust parameters by scaling factors. As a result, the int8-based arithmetics achieve significant improvements compared to the high-precision FP int32 units. Section 1. Problem formulation and approach. The authors identified the inefficiency of nonlinear operations in transformer-based models as a significant challenge. These operations, which often involve high-precision arithmetic, are computationally expensive and hinder the speed-up of transformers on various hardware platforms. To address this, the authors proposed a novel approach that focuses on the interplay between the scaling factor and LUT parameters. They recognized that larger scaling factors lead to less less accurate approximations, and thus the scaling factor in quantization is a crucial element that significantly impacts the precision of approximation parameters. Section 2, Proposed Method. GQA-LUT. The authors introduced a genetic quantization-aware algorithm, GQA-LUT, to automatically determine the breakpoints in LUT approximation for nonlinear functions. This method is designed to overcome the constraints of existing quantization algorithms that fail to adjust parameters by scaling factors. The GQA-LUT is designed to be efficient for hardware design, with compact resource utilization, capitalizing on low-bit integer arithmetic. This approach is a significant departure from previous methods, which often involved high-precision arithmetic and lacked generality. Section 3, Experiment Design and Method Improvements. The authors designed experiments to evaluate the effectiveness of GQA-LUT, focusing on operator-level accuracy for a variety of nonlinear functions. They also evaluated the fine-tuning accuracy of two models, segformer and efficient-VIT, in the context of semantic segmentation tasks under integer-only quantization. The authors further implemented LUT-based PWL with various precision using Verilog HDL and benchmarked their hardware performances, including area and power dissipation. The results showed that the GQA-LUT effectively maintains the fine-tuning accuracy for both models, with minimal loss, and achieves improvements over the previous state-of-the-art work nitrogen mononitride LUT. Additionally, the INT8 hardware PWL units integrated into GQA-LUT yield significant savings in area and power dissipation compared to their high-precision counterparts. Technical results. 1. The proposed GQA-LUT method effectively maintains the fine-tuning accuracy for both segformer B0 and efficient-VIT B0 models. The loss in accuracy is minimal, with only 0.07% for segformer B0 and 0.02% for efficient-VIT B0. 2. When compared to the existing nitrogen mononitride LUT method, GQA-LUT shows significant improvements. The accuracy improvements are 1.07% for segformer B0 and 0.88% for efficient-VIT B0. 3. The INT8-based arithmetic used in the proposed method achieves significant improvements in terms of hardware performance. The area and power performance synthesized with TSMC28NM technology demonstrates that the INT8-based arithmetics achieve significant improvements compared to the high-precision FP INT32 units. Implications of results. 1. The results indicate that the proposed GQA-LUT method is effective in maintaining the fine-tuning accuracy of models while reducing computational overheads. This makes it a viable solution for optimizing nonlinear operations in transformer-based models. 2. The significant improvements in accuracy compared to the existing nitrogen mononitride LUT method suggest that the GQA-LUT method is more efficient in approximating nonlinear operations. 3. The significant improvements in hardware performance with INT8-based arithmetic imply that the proposed method is efficient for hardware design with compact resource utilization. Ablation studies and implications. 1. The paper does not explicitly mention any ablation studies. However, the comparison of GQA-LUT with the existing nitrogen mononitride LUT method can be considered as an ablation study. This comparison helps in understanding the effectiveness of the proposed method in improving the accuracy of models and reducing computational overheads. 2. The implications of this comparison suggest that the proposed GQA-LUT method is more efficient in approximating nonlinear operations and is effective in maintaining the fine-tuning accuracy of models. This makes it a viable solution for optimizing nonlinear operations in transformer-based models. Key highlights of the paper. 1. Key insights. The paper identifies the scaling factor in quantization as a significant element that impacts the precision of approximation parameters. It also reveals that larger scaling factors lead to less accurate approximations. 2. Key contribution. The paper introduces a novel genetic quantization-aware algorithm, GQA-LUT, which automatically determines the breakpoints in LUT approximation for nonlinear functions. It also presents an enhancement technique, which views the fixed point FXP conversion as a mutation process. 3. Key idea. The main idea of the paper is to optimize nonlinear operations in transformer-based models, which are computationally expensive and hinder the the speedup of transformers on various hardware platforms. The proposed method, GQA-LUT, aims to overcome these challenges by capitalizing on low-bit integer arithmetic and managing larger scaling factors effectively. 4. Key results. The GQA-LUT method maintains the fine-tuning accuracy for both segformer B0 and efficient bit BO, with minimal loss of 0.07% and 0.02% respectively. Compared to the previous state-of-the-art work nitrogen mononitride LUT, GQA-LUT achieves improvements of 1.07% and 0.88% for these models. Additionally, the INT8 hardware units integrated into GQA-LUT yield significant savings of 81.3 to 81.7% in area and 79.3 to 80.2% in power dissipation compared to their high-precision counterparts. 5. Key conclusion. The paper concludes that the proposed GQA-LUT method, with its emphasis on quantization awareness and the unique genetic algorithm, surpasses previous methods in both operator-level performance and fine-tuning accuracy. It also highlights the significant savings in area and power dissipation achieved by the INT8 hardware units integrated into GQA-LUT.